Welcome to lecture number 19 of Signals and Systems. So to summarize the previous session, we could learn about the system interconnections and its operations, and we also understood about the relationship between the system properties and the impulse response. We could see around four properties of an LTI systems. Those are memoryless, stable system, then invertible system, and then causal system. And we also learned about how to check that the given impulse response of a system is having the following properties or not. We could learn about conditions for memoryless, condition checking for stability, causality, and as well as invertibility. And we also looked into some numericals, problem solving. Around four examples we solved, and we could understand how to identify whether the given system, given LTI system, is memoryless, causal, or stable. So in this class, we are continuing from the same point on detecting whether the given system is having the properties that has been mentioned just right now. With that, I'll be having one or two examples on finding out the inverse system or invertible system. So with this, let me begin today's class. I am sharing my screen. The topic covered in today's session from chapter 2 time domain representation of LTI systems are relation between LTI system properties and impulse response. This we had already taken in the previous session. Today it is a continuation from where we had left. And the second and new topic that we are starting is differential and difference equation representation of LTI systems. I can say this is part 2 of the chapter 1. So chapter 2, part 2 of the chapter 2. So chapter 2's part 1 is about convolution sum and convolution integral and solving for the system properties for the given system response. Part 2 being differential and difference equation. Okay, so I am having an intention to take only introduction part in today's session. Okay, so here we begin with the problems what we were solving in the previous class. I think I had solved around four examples in the previous class. Let me continue from the fifth example. I was calling it as ABCD. So the next being E. The given example is h of t is equal to e raised to at into u of t. This is a given problem. Now you need to identify whether it is memoryless or not memoryless first. So for that, what you need to do is you need to check whether h of t is equal to 0 for t not equal to 0. If this satisfies, for any value other than t equal to 0, your h of t should be 0. Then only we call it as memoryless. But is it that case? You can check here. It is an exponential term. E raised to at, e raised to at. Okay. So hence, yeah, and there is u of t multiplied. So you will be having somewhat the signal like this. If a is positive, so it will be like this. Okay. If a is negative, it will be decaying. But it is growing till infinity and it has got past values, hence it is not equal to h of t is not equal to 0 when t not equal to 0. For example, when t is equal to 1, I am having some value, hence I write t h of t is not equal to 0. So hence it is not memoryless. Next being, I need to check the causality. Causality's condition is h of t should be 0 for t less than 0. Means it should not depend on any future values. Future values are present on this side, so you don't have any values present here. Hence, what I can say is this is a causal system. This is a causal system because it does not depend on any future value. Now coming to the stability, here you need to concentrate more. So stability condition is integration because it is a continuous time minus infinity to plus infinity range. So h of 2 mod d2. This can be written as integration, and as you have u of t, when you have u of t, the limit changes from 0 to infinity, because u of t is getting multiplied to e raised to at. U of t exists only from t greater than 0 till infinity. Okay, that's why I'm changing the limit. So mod of e raised to a to d2. Okay, so if I integrate it, I would get it as e raised to e2 divided by a. So the limits are infinity to 0. So first I substitute infinity, e raised to a into infinity divided by a minus e raised to 0 divided by a. So if I solve this, you know that e raised to infinity, a into infinity is again infinity, a raised to infinity is, you know, again, it depends on the value a. So what if, I'll write it here, if, you should be very careful because it is generally given, a's value, it has not been mentioned. If a is less than 0, then what happens? A is less than 0 means this is negative. If a is negative, e raised to minus infinity it will become. If it becomes e raised to minus infinity, then this becomes 0 minus 1 divided by a, because e raised to 0 is 1. So you will have the value minus 1 by a, which is less than infinity, hence stable. Now if a is less than 0, the meaning is decaying exponential. That's the meaning. For decaying exponential, it is stable. For example, I'll write it. This is considering a growing exponential, considering a greater than 0. If I consider a less than 0, this would look like this. Fine. Now we have to consider the other one. If a is greater than 0, then what happens? Then it is a growing kind, growing exponential. So in this case, so e raised to, this becomes plus infinity, right? It is becoming plus in, because it is positive, divided by a, e raised to 0 by a. So this will give somewhat infinity minus 1 by a, or else we call it as infinity. Hence it is not stable or unstable. So your conclusion is, so given system is stable only if a value is less than 0. This is how you need to conclude. Should be very careful about the general things that has been given. Okay, I hope it is clear to you. Now next one. The given system is h of n is equal to 2 raised to n u of minus n. Now you know that u of minus n can be written as, this is n, 0, minus 1, minus 2, minus 3. So here it is amplitude 1, amplitude 1, amplitude 1. It grows on till minus infinity. Now you know that 2 raised to n. 2 raised to n means you need to multiply with 2 raised to n. For n is equal to minus 1, h of n, I'll write it as 2 raised to n should be multiplied with this one. So at 0, 2 raised to 0 is 1. So it will maintain it as 1. 2 raised to minus 1 is 1 by 2. So it is 1 by 2 at minus 1. At minus 2, it is 1 by 4. And it continues. So it is like decaying in a discrete time, okay, till infinity. This is h of n. So now you need to identify whether it is memoryless or not. So for that, condition is h of n should be equal to 0 for n less than 0. Is it happening here? H of n is not 0 for n less than 0, or n not equal to 0. N not equal to 0. Okay, so h of n is not equal to 0 for n not equal to 0. So here you have some finite values here, hence it is not memoryless. It is having memory. Now regarding causality, the condition is h of n should be 0 for all the value of n less than 0. But here for n less than 0 you have a value. Hence it is a non-causal system. Hence it is non-causal system. Now then comes stability. Stability, it is a discrete time. Hence you need to use a summation k ranging from minus infinity to plus infinity. Mod of h of k should be less than infinity. Okay. So here the integration k ranging from minus infinity, starting from minus infinity till 0, because from 0 onwards the value is of h of k is 0 itself. Hence I take it at 0. So h of k. So this is the expression for the given problem. Now what we are supposed to do is summation here minus infinity till 0. It is I can write it as 2 raised to in place of n I am writing k. In place of n I am writing k. Now what I do is by inverting sign everywhere, inversion of sign everywhere, inversion of sign everywhere. So everywhere I change the sign. For example, here it becomes infinity. Infinity is a big number. I am writing it here. 0 sign will not be there, so I'll write it here. I have changed the sign. So here also I need to change the sign. This becomes like this. Okay, everywhere I change the sign for simplicity. Now it looks like 0 till infinity 1 by 2 raised to k, or else 1 by 2 raised to k. So for this there is a formula like 1 minus 1 by 2, the upper limit plus 1. Infinity, it is infinity plus 1 means infinity itself, divided by 1 minus 1 by 2. So this will give you 1 minus 0, because 1 by 2 raised to infinity is 0, divided by 1 by 2. So this will give you 2, which is less than infinity. Hence the system is stable. Should be very careful. So a few of people may confuse here. Students might confuse here, like 1 by 2 raised to infinity, how it can be 0. Always remember, when your number is in the range, any number p is in the range 0 to 1, and if you take its square or infinity or whatever raised to power, if you take, the number will be less than the number p. For example, let me take it here. 1 by 2 raised to 2 will give you 1 by 4. It is less than this. For example, 1 by 2 raised to 3 will give you 1 by 8, which is very much less. Similarly, 1 by 2 raised to infinity will be 2 less, which is almost equal to 0. That's why it has been written as 0. I think it is clear to you. The system is stable here. Okay, so I am covering variety of the concept, taking various numerical examples. Now let me take next one, G. So h of n is given by 4 into delta of n. The condition says h of n should be 0 for n not equal to 0, and that is definitely true because you have a delta function here. When there is delta function, it means the value exists only at n equal to 0. So rest everywhere it is 0. Hence it is memoryless. H of n is equal to 0 for n less than 0. This is a condition for causality. Now you can check delta of n may exist only at n equal to 0. So n less than 0, h of n is 0 itself. Hence it is a causal system. It's a causal system. Now coming to the stability, you know it's a constant. It's a constant. So when it is constant, it should be less than infinity. Hence it is stable. You can directly come to the conclusion that it is a stable system. Next one. H of n is equal to e raised to 2n u of n minus 1. Very simple. It's like slight variation on the problems that we solved just now. The previous problem I took it as um, somewhere here, yeah, e raised to 80 I had taken. In place of a I have taken 2. In place of t I am taking n. That's it. So a is greater than 0, right? A is greater than 0. A is greater than 0 means system should not be stable for a greater than 0. Let me check the same thing with this problem as well. So memoryless condition is h of n should be equal to 0 for n not equal to 0. Whether that is happening here, you know that e raised to n is exponential, u raised to n minus 1 will vary, have a step, sorry, it's a continuous time. Let me just erase it. So from 1 onwards, 0 will be having 0 value. From 1 onwards, you will be having amplitude 1. This is u of n minus 1. From here, it goes on getting multiplied with e raised to 2n. E raised to 2n would look like this. It would look like this. For 0, as it gets multiplied, if you multiply it, this goes to 0. From here onwards, it will reach till infinity. So hence, h of n is not equal to 0 for n not equal to 0, because at n equal to 1, 2, 3, you have a finite values. Hence, it is not memoryless. And what about causality? H of n should be equal to 0 for n less than 0. Is it happening? Definitely it is happening. Hence, it is a causal system. Now, regarding stability. Stability, as it is a discrete time, so k ranging from minus infinity to plus infinity. H of k, we need to check. So k ranging from here, it starts from 1. I decided by u of n minus 1 till infinity e raised to 2n. Here it is k, that's why I write k. So e raised to k is a resultant exponential curve and it is ranging till infinity, hence it will reach infinity. So system is not stable. System is not stable. Just one problem. H of n is equal to cos of pi by 2 n u of n plus 3. This is a equation given. Of course it is a discrete time. You know, it would look like cos function would look like, so from here, so it's a discrete time, hence it would look like in the cos fashion itself. So it will continue. So negative side also it will be in the same manner. So I hope you got some idea like how cos signal in discrete domain looks. Okay, it will continue in this fashion. Fine. Now u of n plus 3. U of n plus 3 means u of n shifted 3 times onto the left. From 0 it will come at 3. This is amplitude 1. This is amplitude 1. Even this is amplitude 1. Even this is amplitude 1. This is amplitude 1. It will continue thereafter. So this is how it is given. Now if I multiply from here to here, it is 0, minus 1, minus 2, minus 3. So up till here it will be preserved. Thereafter continuous it will be varying in this fashion till infinity. So that's a given question. Okay. So now we have to check for memoryless condition. So memoryless condition is h of k should be equal to 0 for k not equal to 0. Whether it is happening? It's not happening because for k other values also it is having a value, hence it is not memoryless. So memoryless, to be memoryless, it should be a constant multiplied by delta function. That's it. Now similarly, for h of k, for causality, it should be 0 for k less than 0. Whether that is happening for k is equal to minus 3, minus 2, minus 1, you have a finite value, hence it is not causal because it depends on a future value minus 1, minus 2 and minus 3. It's not a causal system. Now regarding stability, see all the time I'm writing condition. The reason is it is very important. You should not skip it. Okay. So here the range is from u of n plus 3 is ranges minus 3 till infinity because cost will vary from minus infinity to plus infinity. This will restrict the limits. So that's why I'm writing here. So this will give you cos of pi by 2 place of n, I write k. U of n plus 3 is 1 in that range. So for this, if I analyze, you know that it is a mod function. So mod function means cos when I substitute k equal to 0, cos 0 is 1, cos pi is minus 1, but it is mod. When it is mod, it is 1, it is positive itself. Cos 2 pi is 1, so it is 1. Cos 3 pi is, it is minus 1, but if you take mod, it is 1. So at some point, for example, for k equal to 1, cos pi by 2, it will go to 0, but there is a chance of many number of k values wherein your cos of pi by 2 into k will result in 1. So it's as good as you are adding 1, summation is there, it will result in 1, adding 1 for infinite number of times. If you add 1 for infinite number of times, it will definitely result in infinity. Hence, the system is unstable. Okay, so this is how your analysis should go on. So now a few assignments I'll be giving. Assignments regarding the properties identification. Okay, the first one being h of n is equal to minus 1 raised to n u of minus n. This is the first assignment. Solve it for finding memoryless, causal and stability. The next example being h of n is equal to cos pi t. Cos pi t. So these two examples you need to check for memoryless, causality and stability. So this is about the three properties of LTI systems. Now we will take the last properties, that is invertible. So this is important one. So the question goes like this: the discrete time LTI system, I repeat, the discrete time LTI system is described by input output relation y of n is equal to x of n plus a into x of n minus 1. This is the relation between input and output which defines the system. Now question goes like this: find causal inverse system. I'll highlight this, it's important. In system that recovers x of n from y of n. Means you have to check for the system invertibility, and you should find its inverse system. Also check its stability. Now the solution goes like this. So here the given system is y of n is equal to x of n plus a into x of n minus 1. This is a given system. Now to find out the system response or the impulse response, what I'm supposed to do? For finding out system response or impulse response, I need to supply impulse function. What is that impulse function? I'll write it here. If this is a system, if input is x of n, output is y of n. Now if I want output as h of n, which is system response, the input should be delta of n, impulse function. That is what I'm doing. To find out h of n, x of n should be replaced with delta of n. This is what we have learned earlier in earlier chapters. This, if I want to write in the sequence manner, I can write it as 1. This amplitude is a, index is 0. This is how we used to write it. Okay, just for your understanding. For invertible system, you know that h of n, when it is convolved with h inverse of n, it should result in delta of n. This one I had highlighted in the earlier slides. H of n convolved with its inverse will result in delta of n. Okay, so I'm considering that. Now with this equation, this is generalized expression. In this equation, I substitute the above equations what we have found out. So here h of n is there, so I write it here, delta of n. So this equation, delta of n plus a into delta of n minus 1. This is h of n actually, convolved with h inverse of n, which is equal to delta of n. Now what I'm supposed to do is further simplify. So you know that it is a distributive property. delta of n convolved with H inverse of n plus A into delta of n minus 1 convolved with H inverse of n, which is equal to delta of n. Okay, so far it is good. Okay, so next is, you know that delta function, when it is convolved with anything, it gives into that expression itself. This convolved with this, as it is a delta function, it will result in H inverse of n itself. This also we have learned in convolution sum while studying with impulse function, plus a delta of n minus 1. A, I write it, it is a constant. Delta of n minus 1, H inverse of n, means this exists at n equal to 1. So what I do is H inverse n minus 1, here it is 0, minus 1 plus 0, it will result in minus 1. This will result in delta of n. Okay, this will result in delta of n. Hence, therefore, H inverse of n is equal to, I take everything on the right hand side, delta of n minus, this goes to the right, H inverse n minus 1. This is an equation of importance to find out the inverse of the system. And I name this system as equation number 1. I take its reference in the next slide. Now, you observe the question carefully. They have asked us to design a causal inverse system. Inverse system should be causal. Given that inverse system is causal. Causal's condition is h of k should be equal to 0 for k less than 0. Means h of k or h of n, whatever. So it is 0 for all the value or all the negative values. So I use this trick. Applying the above concept in equation 1, what we get is, I substitute for n is equal to 0, H inverse of 0 is equal to, substitute n equal to 0, equal to delta of 0, this is delta of 0, okay, minus a into H inverse of n has been substituted with 0, 0 minus 1 is minus 1. Now you know that causal system says that h of k is equal to 0 for k less than 0. So let me write it as inverse itself, because I am designing inverse system. H inverse of k is equal to 0 for k less than 0. So here the meaning is H inverse of all any negative values, minus 1 is 0 because it is a causal system. H inverse of minus 2 is 0. H inverse of minus 3 is 0. So for any H inverse of minus k, the value is 0. That's the meaning of causal system. Hence this value goes to 0. Therefore, H inverse of 0 is equal to, delta of 0 means at n equal to 0, delta function is, its area is 1, minus this goes to 0, 0 into anything is 0. So therefore, H inverse of 0 will result in 1. H inverse of 0 is 1. Now we have to proceed in the same manner for n greater than 0. For n greater than 0, what I do is, let me consider n is equal to 1 first. For n is equal to 1, I take the equation 1 again. H inverse of 1 is equal to delta of 1 minus a into H inverse of, if I substitute n equal to 1, 1 minus 1 is 0. This is equal to, delta of 1 is 0 because delta function exists only at n is equal to 0. This should goes to 0, then only this area will be 1. So it goes to 0 minus a into, what is H inverse of 0? It has just now we have found out. This is 1. So hence the answer is A. H inverse of 1 is A. Very easy, right? For n is equal to 2, let me check. H inverse of 2 is equal to, again from equation 1, delta of 2 minus a h inverse of n minus means 2 minus 1 is 1. So already we have found out h inverse of 1. So if I substitute, I'll write it here. It is 0 minus a. This is again a. So this will result in minus, uh, this will result in minus not a square, minus a square. 1 second. So here I should have written it as minus a, because 0 minus a into 1 is minus a. So this minus a I have to substitute here. So this is minus a. Minus into minus is plus, a square. So h inverse of 2 is a square. Okay, I proceed with one more variety. Similarly, h inverse of 3 is you will get you will get delta of 3 minus a h inverse of 2. So delta of 3 is 0 minus a h inverse of 2 is plus a square, because we had earlier got it as minus a into this minus a becomes plus a square. Write it as plus a square, which will result in minus a cube. So h inverse of 3 is minus a cube. Now by looking at it, we write the h inverse function in this manner. H inverse of n is you just check here. This is 1 for n equal to 0. For n equal to 1, it is giving minus a. For n equal to 2, it is a square. For n equal to 3, it is minus a cube. So to generalize it, I can write it in this fashion. Just check. For n equal to 0, if you substitute, minus a raised to 0 will give you 1. Minus a raised to 0 is giving 1. So for n equal to 1, minus a raised to 1 minus a. That is what I got, minus a. For n equal to 2, I should get a square. For n equal to 2, minus a whole square is a square. For n equal to 3, minus a raised to cube is minus a cube. So we are getting it. So this is for n greater than 0, because it is a causal system. Or else we can write it as h inverse of n, which is equal to minus a raised to n u of n. So this is the inverse system that has been asked for you to derive. Okay, so the question goes like this: find a causal inverse system that recovers x of n from y of n. That we did. They have asked us to check its stability also. To check its stability, we have to follow the condition. The condition is summation k ranging from minus infinity to plus infinity, h inverse of k mod should be less than infinity. So that we write it as, it is causal system. Hence k ranging from 0 till infinity, u of n will be 1. So I have to write minus a raised to n mod. There is a mod. So when there is a mod, I can write it as k ranging from 0 to infinity. Minus does not have importance, because anyways mod is there. It becomes plus. Anyways afterwards I write it as a raised to n. So when this comes, a raised to k, sorry, a raised to k. This is k. This is also k. When this comes, what you are supposed to do? So for this, you have to again think like, if a is greater than 0 or if a is less than 0, what happens? So a raised to n. So this one, if it is 2 square, 2 raised to 2, 2 raised to 4, 2 raised to 3, 2 raised to 5, 2 raised to 6, it goes on growing. It goes on growing exponential it is, but it is discrete time. Less than 0 means, or else I should have written in this way, in this range, or else we simply write it in this way. We write it in this way. Okay. So for a greater than 1, it is growing exponential. For a mod a less than 1 means this is a range. It is decaying exponential. So decaying exponential converges. Growing exponential diverges. Okay. So here what we have to do is, we have to consider a less than in this range. That's why I take for a less than 1, mod a less than 1, in that range, what happens is this becomes 1 minus a raised to upper limit plus 1, that is infinity plus 1 is infinity itself, 1 minus a. So this will result in 1 divided by 1 minus a, okay, which is less than infinity. It is stable. Therefore the conclusion is system is stable, inverse system is stable provided a mod of a is less than 1, means it converges to 0, or else we call it as, it is also called as absolute summable or summability. Absolute summability means the sum will result in the number which is less than infinity. That's the meaning of absolute summability. Okay, so it is also called absolute summability. This is the inverse system. Next, I have one more last problem. Let me just solve it. This is a example problem of Simon Hekin. So y of n is equal to rho of y of n minus 1 plus x of n. H of n is given by themselves. H of n is rho raised to n u of n. This is a given question. Okay, you need to check whether the system is causal, memoryless, and stable. This is a solution. Now, for memoryless, the condition is h of n should be 0 for n not equal to 0. Either that is happening or not, we have to check. It is u of n. Rho is some value. So when it is u of n, for n not equal to 0, definitely h of n will be having some finite value. Hence this fails. It is not memoryless. Now for causality, it should be 0 for n less than 0. Whether that is happening, that we need to check. So u of n exists only for n greater than 0. So n less than 0, anyways, when you multiply it, you will get a 0 value itself. So h of n does not exist for n less than 0. Means h of n is 0 for n less than 0. Hence it is a causal system. Now finally stability. Stability condition, h of k mod should result k minus infinity, u of n is there, hence I start from 0 to infinity, rho raised to k mod it is. So it is nothing but, so again I have to put a condition. If rho mod of rho is less than 1, then this converges. It converges and achieves absolute summability. So system is stable only if rho is mod of rho is less than 1. So this completes your system properties and relation between system properties with the impulse responses. The next topic, the part 2 of the chapter 2, is differential and difference equation representation of LTI system. Its introduction. I'm covering only introduction in this session. Difference equation we'll be using for continuous time system. Difference equation we'll use it for discrete time system. So we write a general form of linear constant coefficient differential equation. You might have learned in your mathematics, but don't worry, this is very easy topic. So continuous time system, we use differential equation. When I say differential equation, it is continuous time system. The general form is summation. This equation looks so big, don't worry, but when I solve some numericals, it will be easy. Summation k is equal to 0 till n, a raised to a suffix k. Okay, so not suffix, it is subscript. Okay, differentiation with k times y of t is equal to summation. It's a differential equation, okay? Simple differential equation that you have been learning in your mathematics course. bk dk by dtk x of t. Okay, here ak and bk are coefficient of system. Fine. So by looking at it, you might feel the equation to be very complex and all. Let me write one simple example for it. Example for differential equation goes like this. Some constant. Let me take some inductor capacitor things here. dy of t dt. R can be any constant also. Here I'm just taking simply to link it with electronics branch. I'm taking inductance and resistance. D square by dt square of it 1 by c y of t. This is equal to d by dt of x of t. This is example number one. Or else one more example if I want to write. Second example, very simple. It is d square by dt square y of t plus phi into dy by t by dt, d by dt of y of t plus 6 into y of t. This is equal to 2 into x of t plus d by dt of x of t. Just have a listen here. Look here. AK and BKs are the constants. Here there is no constant, means constant 1. Here it is phi. 1 and phi are AKs. A of 2, A of 1, it is A of 0. A of 2 is 1, A of 1 is phi, A of 0 is 6. A0 is 6. That is the meaning of AK. BK means this is 1 means B of 1 is 1, B of 0 is 2. That is BK. Now summation means this plus. I have plus mark on left hand side as well as right hand side. That's why these are summation. Then comes differentiation. This k value is 2 here. This k value is 1 here, 1 here. So this is how it is formed. If k value is 0, I get no differentiation, just as it is the variable. General form of the difference equation. Difference equation. Whenever I write difference equation, it is discrete time system. Remember. Okay, so it goes like this: summation k is equal to 0 till n a k y of n minus k. There is no differentiation because it is not a continuous time. Differentiation integration is applied only for continuous time signals. It is not continuous. This is equal to, if it is not continuous, differential rather than differential, we need to take its difference, that is subtraction. K is equal to 0 till m bk x of n minus k, m minus k, or you can write n itself, n it is. Okay, so the order of the differential equation is n comma m. Order is n comma m. So it represents the number of energy storage devices into the system actually. So let us not worry. So the order is like whichever is greater. If n is greater than or equal to m, then the order is only n. Okay. So normally the equations will be in this manner. Okay. The example for this is example for difference equation is goes like this. The last one: y of n plus y of n minus 1 plus 1 by 4 y of n minus 2. This is equal to x of n plus 2 into x of n minus 1. Here you can check here. Summation means these pluses. AKs means constant is 1, 1 constant, 1 by 4. These are AKs. BKs means constant 1. This is 2. These are BKs. Y of n minus k means y of n minus 0, y of n minus 1, y of n minus 2. Here x of n minus k means x of n minus 0, x of n minus 1. So these are the general form of difference equation. So I repeat once again: difference equation for discrete time signal, and the other one is for differential equations. Continuous time is for differential equation. So with this, we will conclude today's lecture, and we'll see you in the next class with more of solve problem solving with differential and difference equations in the next class. Thank you.